Okay. So last time we have discussed canonical ensemble for classical systems. Also, I remind you, the problem is essentially to find the density of the phase space, and by Liouville theorem, we know that this must be a function of the Hamiltonian, and essentially this function. Hello. This function for the canonical ensemble is the exponential, where yes, you have a normalization constant. Okay. Okay, so so in the end, so this is for the canonical ensemble. So the canonical ensemble for a classical system, this is the distribution in the phase space. And so the practical recipe, which one has to follow, is to compute the partition function. So the partition function is a function of the number of particles, the volume, and the temperature. And this integral here e to the minus Hamiltonian divided by kt. And then I have to divide it by h to the 3n times n factorial. And I remind you that this h to the 3n comes because so this is a dimensional number, and h to the 3n is essentially the volume of a single microstate, which can be, potentially be distinguished on the basis of Heisenberg uncertainty principle. And this n factorial is here because when we count the state classically, we should take into account the particles are indistinguishable, or that we don't want to distinguish microstate which differ only by reshuffling of the particles. Okay, so in order to do this, and because otherwise we would have problems of the type of Gibbs paradox. Okay, we would find out that the entropy is not extensive, etc., etc. So this factor n factorial is the same motivation of which we discussed for the Gibbs paradox. Okay, so once you compute this number, then you can compute the Helmholtz free energy. Free energy. Which is just A of n v n t, which is given by minus kt times the log of Q of N, V, and T. Okay, and then once you have this Helmholtz free energy, you can compute everything of thermodynamics. Okay. Now, what we have done last time is to discuss the simplest case, which is that of the ideal gas. So for the ideal gas, classical gas, so the Hamiltonian is just the kinetic energy, sum over the particles of pi squared over 2m. And then these integrals are, so the integral of the volume is very easy to do. It's just the volume. The integral over Q is just the volume to the power n. And the integral over the momenta is just a collection of Gaussian integrals. So what you find is that you can write this as 1 over n factorial times a partition function for one single system, for one single particle to the power n. Okay? And the reason why you can do this, where this Q1 of V and T is just volume divided by H cube times the integral of the momenta of a single particle, which just give 2 pi m kt to the 3/2. Okay. So the reason why you can write the partition function of n particles as 1 over n factorial times the partition function of a single particle raised to the power n is that the particles here are non-interacting. They don't interact, so that all the integrals on all the different particles can be factorized. You can take a different factor, and then you have n factors which are the same, and each of them is the partition function of one single particle. Okay? And this is true for all non-interacting systems. In all non-interacting systems, the Hamiltonian is the sum over the different particles, right? And then the e to the Hamiltonian divided by kt is can be factorized over the different particles, and then I can always do this integral over the different particles, factorize the integral over the different particles. And so I will always have this form of the partition function. Okay? Yeah?
This formula proof for system or two different, okay, if you have two different
Okay, so if you have two different kind of particles, so imagine that, for example, you have a mixture of two gas, one with mass m and one with mass m prime. Okay, so imagine so that you have a mixture of two gases. So the Hamiltonian would be the sum over the first type of particle. Let's say we have n1 particles of type 1 with mass m1, and the second one is n2 particles with mass n2. Okay? Now, what we have to do is, now what is the function, what is the partition function that we have to compute? So the partition function that we have to compute is one where it will depend on the number of particles of gas of type 1 and type 2. Okay, so it will depend on N1 and N2, on the volume, and on temperature, right? So now, instead of 1n factorial here, you will have n1 factorial times n2 factorial, because you don't distinguish states. You distinguish the states where you change the position of gas of type 1s with the position of, you interchange particles of different types. Okay? So if you have a configuration where, if you have a given configuration of the gas, and then now you start exchanging the particles of type 1 with particles of type 2 and vice versa, then this will lead you to a different configuration. Okay? Whereas if you just permute the particle of type 1 among themselves and the particle of type 2 among themselves, since the particles are indistinguishable, so these are not different configurations. Okay? So this is why here we should put 1 over n1 factorial, n2 factorial, and we should not put 1 divided by n1 plus n2 factorial. Is this clear? No. Okay. No, okay, so here we are still discussing classical systems. Okay, we will discuss quantum systems. So there are different effects which we will discuss. Now we are discussing a classical system, classical systems, and so an example of the question you were posing, where when you have two different types of particles, is gas, for example, with two molecules, different molecules with different masses. Okay? So I can distinguish molecules of one type from the other by just measuring the mass. Okay? Okay? So the particles of type 1 are distinguishable from particles of type 2, but particles of type 1 are not distinguishable among themselves, and particles of type 2 are not distinguishable among themselves. So the number of different really different configurations should in order to account to compute the number of really different configurations, I should put this factor here, which eliminates, say, the problem that when I compute a partition function, when I'm computing this integral, I'm distinguishing configuration where particles of type 1 are in different positions. Okay. So I should have this factor here, a factor h to the 3n1 plus 3n2. And then here there should be an integral on dq1 on all the position of particles of type 1, all the position of particles of type 2, all the all the position of particles of type 2, the momenta of particles of type 2, e to the minus h of q1, well, h divided by kt, okay? Now you see, if you compute this partition function here, you see that you can write it in the following form, because you have 1 over n1 factorial. And then you can group all the integrals. So this Hamiltonian is a sum of the two Hamiltonian of the two systems. So you can factorize them. Within each system, you can factorize it in every particle, on all the particles. So effectively, you can write this as 1 over n1 factorial times a partition function with one particle for system of type 1 at temperature at volume V and temperature T to the n1 times 1 over n2 factorial times the partition function of one single particle of type 2 of in volume V and temperature T.
It's just the sum, because in the partition, the expression of the partition function we have 1 over n factorial. So it's just the sum. It's the sum.
You say here I should have n1 plus n2 factorial.
No, in the last line, yes.
Yeah?
It's not 1 over n factorial, because in the expression of q,
n1.
no, have to remove n1 factorial and n2 factorial. Yes,
Ah,
is that-
do I have to remove it?
no, because in the expression of q we have 1 over n factorial.
Yeah. Yes.
So if you put it there, we cannot obtain the q, because in the expression of q we have
Yes. So this is for an homogeneous system, no? This is what you have to find to do for an homogeneous system of identical particles, where you have n identical particles, and you have to put this n factorial here, because otherwise you would be counting differently microstate which only differ by permutation of the particles. Okay.
what I'm saying. Let's write the expression for q1 for example.
Q1.
Yes.
So Q1 of 1 will be just this expression with mass equal to m1.
Oh, if you want to use this one, yes.
This one?
Yes. Q1 will be.
Q1 is just is exactly that, no?
Yes, but with n1 factorial.
N1 factorial. Yes, okay.
So
N1 factorial is equal to
no. Okay.
N1.
Yes, here. If you want to use this formula here,
Yes.
you want to compute Q1 is Q1 equal 1 over 1.
No, wait. N equal to 1.
Yes. No,
So-
N1.
N1.
Yes.
Okay.
N1
Okay, yes. Indeed, what I'm writing here is that the partition function, if I have two different systems, should be Q of N1 times Q of N2.
Yes, with this factor.
Yes, exactly, which is this one.
Yes, if we include this factor, we don't have to write it here.
No. Why? Sorry, so let me do it. I don't understand. So do you agree that the combined system, so the partition function in that case should be Q of N1 of volume and temperature times Q of N2 of volume and temperature?
Yes.
Okay? Okay, so what is this? So this is 1 over n1 factorial times all these integral dq1, dp1, e to the minus h1 over kt. Okay? H1, I call this H1. Okay? Huh? Ah, the Planck constant, you're right. H to the 3n1. Okay? And then the same thing, 1 over n2 factorial, h to the 3n2, the integral dq2 dp2 e to the minus h2 over kt. Okay? Now this, just because of the calculation, is 1 over n1 factorial times a q of one single system. Let me call it q1 of one single particle in volume V at temperature T to the power n1. One single particle. And then this is exactly equal to this. Okay? Okay? Very good. So, so this is the general, and then of course you take the log, and you have the free energy, and you can compute everything. Okay. Okay, so one question here is, which arises here is, if you think about what we have been doing in describing the canonical ensemble, what we have been doing is to say, well, I don't want to study, I want to study a system in thermal equilibrium which has an average energy which is equal to, in this case would be an average Hamiltonian, which is equal to U. Okay? And well, in general, the way we have written this was that was the sum over all the states of ER e to the minus beta ER divided by sum over R ER. Okay? So in the canonical ensemble, so let me remind you about the notation here. So we have been studying about a system which can be in many different states, labeled by R. Each of these states has energy ER. And we have asked what is the probability distribution, what is the generic probability distribution over these states such that the average energy, what is the probability PR of state R, such that the average energy is fixed, is equal to U, but the energy can fluctuate. Okay? And, we have said this is essentially a description which will apply to a system in thermal equilibrium. And then we have seen that the form of this PR is given by this form here. So this is PR. Okay. And that beta is 1 over KT.
We don't have ER in the denominator, right?
We don't have ERs. Yeah. Otherwise, this is 1. Yeah. Okay, so Now the question is, and once we do all of this, then we can compute in the end. We have a recipe to compute the Helmholtz free energy and to compute all the thermodynamic relations. Okay. However, one important thing is that the thermodynamic relation, the relation between physical quantities which we get from this procedure, should be the same as those we derived from the microcanonical ensemble, where we were fixing the energy and we were computing the entropy and then compute thermodynamics from the entropy. We must have the same description. And if we must have the same description, it must be that even if when I'm considering this system where I'm not strictly fixing the energy so the energy here can fluctuate from 0 to, well, from minus infinity to plus infinity in principle. So it must be that in this particular distribution, the energy does not fluctuate very much. And actually it does not fluctuate essentially at all. Okay? So that in order to show that the description which we get from the canonical ensemble is essentially equivalent to the description which we have from the microcanonical ensemble, what we have to figure out is what are the fluctuations of the energies. Okay, so how, I mean, if I measure, so what is the probability that I will find my system with an energy which is very different from this one, okay? So in order to compute the fluctuations of the energy, one trick is the following. Let us take the derivative of this equation with respect to beta. And so if we take the derivative with respect to beta, you see that up here you have a term which is minus ER times minus ER, which is essentially minus the sum over R ER squared times PR. Okay? So this is the term where you take the derivative here. There is a term ER squared, and then what remains is just PR. Then the other way I should take the derivative is here. Okay? So what I would have is just essentially the sum over R of ER times PR all squared. Okay? Because, well, I have a minus sign because I'm taking the derivative down here, another minus sign because I'm taking the derivative of this. So this will be squared, and I will have also the numerator squared. Okay? So all I will have is all of this squared. And now you look at this equation, and you find that this is really the variance of the energy, with a minus sign. Okay? So this is minus the fluctuation of the energy squared minus the average of the energy squared, or which you can write as, say, let me write it as the average of the square fluctuations of the energy. But this average is the average over this probability distribution here, okay? But what I can do is also to do this, to take this derivative using thermodynamics. So what I know is that if if U is the energy of my system, then this derivative is also equal to dt d beta times du d t. And since beta is 1 over kt, this is minus 1 over k t squared, and sorry, so I should write that dt is 1 over k beta square beta, no? So the derivative of t with respect to beta is 1 over beta square, k beta squared. And then the du dt is just the specific heat constant volume. So this is just minus k t squared times cv. So if you now, here there is a minus sign. So if you compare these two equations, you get a very interesting result. You get a very interesting result that the fluctuations of the energy are equal to k t squared times the specific heat. Okay? Very good. So now if you look at the relative fluctuations of the energy, so these are the fluctuations of the energy. So if you want to a measure of how much the energy fluctuates, you should compare this to the average energy. Okay, so you should compute the typical fluctuations of the energy, which are the square root of the variance, and you should compute the relative fluctuations. Okay. So these relative fluctuations are clearly equal to k t squared times, t times the square root of k times cv over u. And the important thing is that now a specific heat is extensive, the energy is extensive. So all of this is of order 1 over square root n. Okay? So if I take a very, very large system, the relative fluctuations of the energy will be extremely small. So that even if the energy is not fixed in the probability distribution, in the probability distribution, I will only observe values of the energy which are essentially equal to the average energy, and the deviation which I will observe from that, in relative deviation which I will observe from that, is over the 1 over square root n. Where square root n is always very, very large, n to the 10 to the 23. So essentially, I will not be able to. I mean, it's very difficult to see any fluctuations in the energy now, or in the macroscopic system. Okay? Now, I would like to give you a little bit more of insight into why this is so. So let us consider, as we said, we can say that the probability to observe a particular system in the canonical ensemble with a given energy E can be written as, say, a density of states times e to the minus beta times E. Okay? So this is generally the way in which you can write the probability of a certain energy E. So you can think that every time you look at the system, you are drawing a random energy from this distribution. Okay? So it must be that if the fluctuations of the energy are very, very small, so this probability distribution must be very, very concentrated. Okay? So it must be, and indeed you can figure out that generally if you plot, so this function here, the density of states will be a very fast increasing function of the energy, because the more you increase the energy, the more states you can accommodate. Okay, so G of E will be very, very fast increasing. E to the minus beta E is a very fast decreasing function instead. So the product, when you make the product between the two, there will be a maximum. There will be likely a maximum in between. And this maximum will be at some energy E star. Okay? So what I want to show you now is that essentially this maximum E star is essentially equal to the average energy. Okay? And so if you want to find this maximum of E star, what you have to do is to look for the maximum of this function here. So let's look at the maximum of the log of this function. So I should take the derivative with respect to E of the log of PDE, which is the derivative of log of GDE with respect to E times E to the minus beta E minus beta times the same. No, sorry, minus beta. No, what am I doing? Minus beta. So this is the equation I have to solve, right? So the log of this is the log of G minus beta E. So the derivative is just the log of G of E divided. Okay, so the solution of this equation is will give me the maximum, and you can see that the solution of this equation is where the derivative of the log of G of E divided by dE at E equal E star is equal to beta. And you know, in the we have said that this is nothing but the number of energy of microstate with energy E. Okay, so this is 1 over K times the entropy. Okay, so this is in the microcanonical ensemble. So this is really the 1 over K times the derivative of the entropy with respect to the energy at E equal to E star. okay? And this is equal to beta, which is 1 over kt, okay? On the other hand, in the canonical ensemble, we know that this is true, so that the temperature, so the derivative of the entropy with respect to the energy, when the energy is equal to U, is equal to 1 over T. Okay, this is the thermodynamic relation which you get from this thermodynamic potential. Okay, so and so it must be that if these and these are true, it must be that the energy U is equal to the energy E star, or essentially that there is no real difference between E star and U. Okay. Now, let's. So we can see this for the ideal gas. For the ideal gas. So for the ideal gas, we have found that the Qn of V and T was 1 over n factorial. Then there was volume divided by H3 to the n, and then 2 pi m kt 3 half, right? Is 3, and there is n, 3n over 2.
Why much GD max last expression?
This one?
No, yes, the free expression. Just
So what I'm saying is that, well, we are looking for the maximum. You call A star the maximum. So the condition that this is maximal is telling you that the log of G of E, the derivative of this at E star must be equal to 1 over kt. Okay. But in the microcanonical ensemble, we know that this is the number of microstate with energy E. So its log is entropy divided by K, right? And this derivative at E star, so in this equation, they tell you that the derivative of the entropy with respect to the energy at E star is 1 over T, okay? But then in the canonical ensemble, you have that the temperature is the variation of the entropy with the energy at U. So if this equation and this equation are satisfied, it must be that E star is equal to U. Okay? Now, and we have also seen that we have seen that essentially this is the integral of this object is the integral over the energy of G of the energy e to the minus beta times the energy. Okay, so that you can essentially write the partition function in this way. Okay, so now what I want to find out from this equation is what is G of E. Okay, now in order to do this, this is KT is just 1 over beta. So you see this Qn, apart from other things, is proportional to beta to the minus 3n over 2. So if I make a change of variable z is equal to beta e in this integral here, then what I have is that this is 1 over n factorial times 1 over beta times an integral in dz of g of z divided by beta of e to the minus z. Okay, so you see the Qn should have this behavior with beta, should be proportional to beta to the minus 3n over 2. And this behavior should be accounted for by the behavior of g as a function of z. Because there is, I mean, apart from this 1 over beta here, there is no other point where beta enters here, okay? So it must be that g of e is proportional to, well, it is some constant, say g0 times energy to the 3n over 2 minus 1, okay? So if you have this behavior here, then you see that the behavior with beta from this equation will match this one, okay? Now you see, indeed, this is a function which is, since n is very, very large, this function is a very, very fast increasing function of the energy, okay? So this is really very, very fast increasing function of the energy. However, it is important that this is increasing slower than exponential, okay? Because if it was increasing faster than an exponential, or as an exponential, then the probability distribution will not be normalizable, okay? There will not be... this is increasing as a power of the energy, so slower than exponential. So it is so that there is actually a single maximum there, and actually you can. It is possible to work out. It is possible to work out what the probability distribution of the energy will be, because from since there is a very, very sharp maximum, what we can do is to take the log of the probability of the energy and to expand it around the maximum. Okay, so the first term is log of p at E star, which is equal to u plus the first term, since it's the maximum, will be equal to 0, so there is no linear term. And the second term will be 1/2 the second derivative of the log of p with respect to E squared at E star times E minus E star squared plus higher order terms. Okay? Sorry, this is the higher order terms. So the first thing is this one. So in this one, there is the log of G of E star, which is 1 is 1 over k times the entropy. This is the log of G at E star. Then there is minus beta times the energy. And then, yes. And then, so the second derivative, now the second derivative of this, well, we can argue that this will be the derivative with respect to the energy of the first derivative with of the derivative, well, of S divided by K minus beta. So the derivative with respect to this, sorry, so the log of P is S divided by K minus beta E. So I have to take two derivatives with respect to the energy, right? So the first derivative will give me so the first derivative of the entropy with respect to the energy would give me 1 over the temperature. Okay, so wait a moment. No, this is not the right way to proceed. Because I should not so if I compute this second derivative, then I should compute it at E star only at the end. Okay, so only at the end I should put this equal to E star. Okay, so the first derivative will give me, so beta is just a number here. Okay, so the first derivative will give me 1 over kt, and here I will get minus beta. So in the second derivative with respect to the energy, this beta is a parameter, is the parameter of the distribution, whereas this T is related to the dependence of the entropy with respect to the energy. So I have only the first, the derivative of this term here, so it's minus 1 over kt squared times the derivative of the temperature with respect to the energy, and this is 1 over the specific heat. Okay, so this is minus 1 over kt squared times the specific heat. Okay, so this is this term here. So the log of P of E, there is a minus sign, so it's minus E minus E star squared divided by 2 kt squared times CV plus higher order terms. So, and you see the distribution of the energies. So this term here is a constant. Is actually you can use the relation that A is equal U minus T times S. And so with this relation, essentially you see that beta times A is equal to beta U, or well, this E star is equal to U, no? So minus 1 over K times S. So this is actually minus beta times the Helmholtz free energy minus E minus, well, the energy, average energy divided by 2 kT squared Cp. Okay, so what you get in the end is that the distribution of this distribution of energies in the canonical ensemble is very well approximated by a Gaussian distribution of this form, with a variance which is given by exactly this result here. Okay. Okay. Now I want to start discussing one very general result in statistical mechanics, which is called the equipartition theorem. Okay, so this theorem is results from a very, very general identity which we can use. We are again we are discussing classical systems. Okay, so we are discussing again a classical system. So classical system, I will have an Hamiltonian which depends on the coordinate and the momenta of 3n coordinates, 3n momenta, and so let me call. So in general, it will be a function of a set of coordinates, and x is a vector. Coordinates x1, x2, up to x, for example, 6n for a gas. Okay? For a gas, I mean, there will be. So you may imagine that these are either the coordinates or the momenta. Okay? Now, what I want to do is to compute the derivative of the Hamiltonian with respect to one of the variables, xj, multiply by variable xi, and then compute the average in the canonical ensemble. Okay, so this is the expected value on the canonical ensemble. So it means essentially that what I want to do is the integral on all the x values, all the coordinates of xi dh. So this is d6n, okay, x. dxj times e to the minus beta h divided by integral dx 6n of e to the minus beta h of x. Okay? This is just the expression of the expected value of this function here. Now I can use a trick. Take this integral up here. And this integral up here, I can write it as in this form as xi times the derivative with respect to xj of say minus 1 over beta of e to the minus beta h, right? So if you take just the integral up here, this is equal to, so this part is equal to this, okay? Because when I take the partial derivative of e to the minus beta h with respect to xj, I will have e to the minus beta h times the partial derivative of h with respect to xj, and I have a factor minus beta, which cancels that. Okay? Very good. Now what I can do is to take an integral by parts here. So that is, I take, I do the, I mean, these are 6n integrals. So I will do the, I have minus 1 over beta. And then I have 6n minus 1 minus j. So all the integrals which do not involve variable j are these ones. And then in variable j, I do an integration by parts. Integration by part means that, well, I have the term where there is xi times e to the minus beta h of x. This will be computed in, well, xj, now let me assume that it can take some extreme value between x minus and x plus. And then I have the other term of the integral by part, which is the integral on dxj of e to the minus beta h times dxi divided by dxj. Okay? Now the first thing is I will assume that as the coordinate xj goes to the extremes, the Hamiltonian, either the potential energy or the kinetic energy, goes to infinity, so that essentially this the finite part of the integral is 0. Okay? And the second thing is that here the partial derivative of xi with respect to xj is the delta ij. So it's going to be 0 if I is different from j. It's going to be 1 if I is equal to j. Okay, so this is the Kronecker delta. So what I will have is minus and minus. I have delta ij divided by beta times an integral. And the integral which I'm left with is just the integral over the other coordinates and the coordinate xj, which is just my integral over all the 6n coordinates of e to the minus beta times h. Okay? So this, so the integral up here is equal to this. Okay? Which means that this expected value here and this integral is equal to what we have at the denominator. Okay? So that what you find out of this is that this expected value is equal to delta ij divided by beta, or kt delta ij. Okay? So this is a very, very general relation which holds in classical for classical systems. Okay. Everything clear? Okay. So now imagine that you have an Hamiltonian. Yeah. No, this is not the average energy of one part. It is well, if no, it's not the average energy of one particle, right? Sorry? No, we are going to relate it to physical quantities. Yes, this is. It's just a mathematical identity. Okay. It's a mathematical identity. So now imagine that I have an Hamiltonian a system. Imagine that I have a system which can be described in canonical coordinates by a quadratic Hamiltonian. So imagine that the Hamiltonian of my system is really a sum over the particle of some ai times momentum squared plus bi times. So this is, for example, an harmonic oscillator. Okay. So in this case, if you compute, say, for example, the derivative of h with respect to pi and multiplied to pi on pi, what you will have is exactly twice ai times pi squared, right? And if you do the same with q, qi times dh dqi, you will have just twice bi times qi squared. Okay, which means that now if you take the sum over I of pi d dpi qi d q of the Hamiltonian. If you combine these and these, and you take the average of this on the canonical ensemble, if you combine this equation and this equation, you will get just twice the value of the expected value of the energy, so twice times the energy, the average energy. Okay. However, now if you take this relation here, then the expected value of all these terms will be equal to kT. Okay, so that here you will get kT times the number of degrees of freedom. Let me call it F. Okay, so this F is equal to number of degrees of freedom. So, for example, this would be equal to 6N for a gas. Okay. So what this tells you is that for this system, the average energy is 1/2 is F times kT divided by 2. Okay. In particular, you see, if you have an Hamiltonian which has a part, imagine that you have an Hamiltonian which is this plus another part, okay? Another part, let's call it H tilde. And you want to compute what is the expected value of this part of the Hamiltonian. Then you can use and imagine that so this part does not depends on other coordinates, okay, which does not depend on the Q and the P which enter in this part of the Hamiltonian. Okay, so if you have some degrees of freedom which are only which enter only quadratically in the Hamiltonian, then you can repeat this calculation here, and you will have that the contribution of the energy to the energy of the degrees of freedom which enter quadratically in the Hamiltonian can be computed in this way. Okay, and this tells you that each degree of freedom which contributes quadratically to the Hamiltonian will contribute to the Hamiltonian by an energy which is kT divided by 2. And this is called the equipartition theorem. Okay? It tells you that all degrees of freedom which enter quadratically into the Hamiltonian give a contribution to the energy which is kT over 2. Or if you want, they all give a contribution to the specific heat, which is the derivative of the energy with respect to temperature, which is K over 2. Okay? Yep.
Why we specifically work with those quadratic terms?
Because, well, for quadratic terms are quite frequent. So, for example, the non-relativistic kinetic energy is it's a quadratic term in the Hamiltonian, right? And also in many classical systems, so the Hamiltonian is the part which depends on the momenta is it's quadratic, no? And also in many cases you can use I mean, an Hamiltonian which depends on coordinates quadratically as an approximation, as a first order approximation of a more complex Hamiltonian. No, so that this and for all the degrees of freedom which enter in this way, quadratically in the Hamiltonian, you know what they will do. You know what they will, how much they will contribute to the energy, to the specific heat. You know what is. You have this very general result, okay, which tells you what. No.
So can we use this thing for other like combinations of how many times coordinates? Like if we
Yes. So in general, you can do all canonical transformation to the variables and go from one set of dynamical variables to the other, and of course there are sets of coordinates which will make the model simpler, and or for which some particular coordinate will be quadratic, so that that will give you some insight on how the system, your system is behaving. No? Other questions? Okay, so of course I remind you that this result, the equipartition theorem, only holds for classical system. Classical systems, I mean, it also holds for. It's very general in the sense that it holds for any Hamiltonian. But it also only holds for classical systems. For quantum systems, what we will see is that this equipartition theorem is a good approximation at high temperatures, because that is at high temperature the classical approximation, the classical way of counting microstate is approximately valid, whereas at low temperatures the way of counting the microstates is not valid. So in particular, this you see this, for example, one contribution, so this tells you that there should be a contribution which is equal to the kinetic energy, let me call it K. For classical non-relativistic systems, should always be equal to 3n kT over 2. Okay? So that the energy should be, because any Hamiltonian, any classical Hamiltonian or a classical system will have a kinetic energy which is equal to sum over I of EI squared over 2m plus, say, an interaction energy which depends on the moment. So since you have so the expected value of this part, which is the kinetic energy, since this is quadratic, will be equal to 3n half kT. Okay. So this tells you in particular that the specific heat will have a contribution which is constant at all temperatures. Okay, so maybe there will also be another contribution from the potential, but there will always be a contribution of the specific heat, which is 3n k divided by 2. And in particular, even at very low temperature, even at zero temperature. And that is clearly wrong, in the sense that the specific heat also typically goes to zero as the temperature goes to 0. And this is because you should think of, we have seen today that the specific heat is related to energy fluctuations. It's related to fluctuations of the energy. And you can decompose the fluctuations of the energy in the fluctuations of different degrees of freedom. Okay? So what happens in quantum mechanics is that, say, for example, when you quantize a classical system, so the energy level becomes discrete. So you have a finite number of occupation of way to occupy the energy levels, and at 0 temperature, few of these energy there are few ways to occupy these energy levels, which contribute, which is as if the different degrees of freedom are essentially frozen. Okay, and so if they are frozen, they will not contribute to the fluctuations of the energy, and they will not contribute to the specific heat. Okay, we are going to see this even for ideal gases in Fermi statistics and in Bose statistics. Okay. Okay, so I think probably it is a good place to stop. If you have questions, is everything clear? So as an example, what we will do next time, so an example of a system for which we can apply this theorem is the classical harmonic oscillator, or a system of classical harmonic oscillator. So for this system, the Hamiltonian, you can think that the Hamiltonian is just the kinetic energy plus an elastic energy and so I mean, you can consider this as a completely artificial system, but you can also consider this as an Hamiltonian which describes, for example, the small oscillation of atoms around the crystalline positions. Okay, and so this is this can be a first model to study thermal properties of solids. Okay, to study the and then in that case, you would think that each I would run on crystalline lattice, and on each position I of the crystalline lattice, you have a different atom, and this is the oscillation of this atom around its equilibrium position are described by say an harmonic oscillator, or indeed by 3 harmonic oscillators along the 3 directions, along the 3 dimensions. Okay, so this is and of course you see this is clearly we will discuss this. We will do all the calculation for this system next time. It's rather simple. You can also do it as an exercise. But you see that for this Hamiltonian, we can directly say that the energy at a given temperature will be equal to, so each of these, each particle will contribute 3/2 kT from here, 3/2 kT from here. So it will just contribute 3, so the average energy will just be 3n kT, okay, by the equipartition theorem. Okay. And so the specific heat of this solid will be 3nk, okay. But maybe on Friday we are going to check this result, do the calculation in full glory. Okay? So see you on Friday, on Wednesday. Yes, Wednesday at 9. Okay?